here. Hannah and Maggie, nice to have you join us. We've been covering a lot of logistics. I'm going to freeze the screen because they're taking notes right now. The logistics that I was covering had to do with, wait, we just took a test on Chapter 9 and we're still in Chapter 9? We are still in Chapter 9, but a different Chapter 9. We're in someone else's textbook, Chapter 9. We're in, oh my goodness, it's CalcChat. This book's Chapter 9. Why? Our book condenses things more than it should sometimes, especially when it's something new that we need to learn. Well, so in Google Classroom, for Chapter 9, there was Chapter 9, sequences, L'Hopital's, improper integrals, a weird mixture of all sorts of topics that kind of made sense when put together. But now there's going to be a new Chapter 9, and the new Chapter 9, I actually have to write it, is not going to be sequences, L'Hopital's, and improper integrals. The new Chapter 9 I'm going to call Chapter 9 OT, other textbook, or ISA as you like to affectionately call it. He whispered it, overtime. Is going to be convergence, if you guys are titling your notes, and divergence of series. Series, convergence, and divergence, or the convergence and divergence of series from another textbook so that our Chapter 10 does not kill us. We need to do the other book's Chapter 9. In your Google Classroom, I do have a copy of the PDF that has all the homework exercises for this chapter. We are starting in section 9.2, but every single section homework is going to have you go back and do some from an earlier section, hence why I put section 9.1 in there. Because in your homework, you're going to notice it's like, hey, here's section 9.3. By the way, go back and practice 9.1, 9.2. Hey, here's section 9.4. By the way, go back and practice 9.1, 9.2, 9.3. I need you guys to know each of the previous sections as we go to a new section. So I'm going to be spiraling some review in there. It is technically in your shared class folder also if you guys want to access it in the handouts. Handouts, assignments under Chapter 9 OT. And I'll try to get some sort of like PDFs of the actual sections if I can figure it out. If you want it, or I have a textbook in my room. And I need water. Oh my goodness. One of these days, I'll be able to speak again. All right, here we go. 9.1. What was the title from the other book one more time? Sequences. So before we technically start section 9.2 in the other book, let's do a quick, frozen recap. I'm losing my mind. Here we go. Quick recap of what's important from the sequences that we talked about in our section 9.1, which is why we're not doing their section 9.1. Kiddos. Oh no, it just disappeared. I don't understand. There we go. How do we determine the convergence or divergence of a sequence? Not serious. What happens? If it equals L, then what's true? If it equals infinity, or negative infinity, or oscillating. Are we good? Sweet. I'm going to change the page real fast. Although I'm hoping the people taking the test already knew that, so I didn't help them that much. But now we're figuring out convergence and divergence of series, not sequences. Oh, thank you. Do you guys remember what a series is? Yeah, it's a summation. No big deal. It's a summation of, who's that? Oh, so it's just a sequence with addition signs, right? Okay. But what about the partial sums? That's the infinite one. That's just ... Easy cheesy. But what about the partial sums? S sub 1, first partial sum, includes how many terms? Just one. S sub 2, Second partial sum includes how many terms? Third partial sum, the sum of the first three. In order for a series to converge, we're going to write it down in just a second. Guess what needs to happen to the partial sums? They need to converge too. Check out that notation at the very bottom. We've just been doing improper integrals. In improper integrals, you need to replace the infinity with a constant and then have a limit on the side. True? Okay. So then what if awkward pause for those of you not with us and not in class because I'm giving the bonuses for the people taking the test. Okay. I can only multitask so much. I try. What happens if we're looking at a finite sum instead of an infinite sum? Guess what we can replace him with? All of his partials. So when we're trying to figure out whether or not an infinite sum exists, or I should say converges or diverges, we need to look at the limit as n goes to infinity of the partial sums, and that's where things get tricky. Now, quick recap. I just want you guys to go ahead and do a recap of using your calculator with series. Do you know how to use it? I don't know if you necessarily need to write all the beginning stuff down. We've already done this once before, but do you remember how to use it? Sequence mode. We've done that before. Oh dear, guys, we had like a whole class period. Yes. Yes, we've gone into sequence mode. Have we made things like n min? U of n, what does that stand for? What does that represent? No, he's not the initial. U of n? Remember, it's function notation for the nth term, right? U of n, V of n, W of n. I don't remember exactly what letters are used. I know it's U and V when you're in your y equals in sequence mode. U of n min is the initial. Good, Aryan. So we have the lower limit is the n min. We have the U of n is our nth term, and we have our U of n min is our initial. Don't worry, no Fibonacci that we're going to have to be worrying about. And then number 5 says check your graph or table. Sorry for the lack of indentation. Let me go fix it. Why am I giving you this before we've covered any convergence or divergence tests? Because there might come a point where you are like, I don't know. And you're just curious the convergence or divergence. If you're allowed to use your calculator, you can technically plug it in and go to 10, go to 100, go to 1,000,000, and see if you can figure out what's going on as far as whether or not it's actually converging. At the bottom of this page, it's asking for prediction. Calculator time. Does every group have at least one? I have the first two done for you. What I'm going to want you guys to do in just a second are the second two. So let's peek at the first two. I think I have little copies of what the calculator would show. Let's see if we can kind of understand how to think about, how to ponder, how to predict. But I won't necessarily be able to tell you today for each of these. Well, actually I could tell you for all of them as to what's truly going on and whether or not our predictions are right or not. Number 1. Does it make sense how I put this sigma, this summation into, oh, wait, you can actually put a sigma in your calculator? Yes. How do you find sigma? We didn't do that last chapter. We were doing sequences, not theory. Now we're doing theory. How do you get it? You can go to math and you can scroll down to summation, or there is a shortcut, alpha window, I think. Is it alpha window where there's a sigma? I think there's alpha window where there's a sigma. You're going to go from 1 to n because ours goes from 1 to infinity. Of course we can't plug in infinity, but we can plug in n. I'm going to do negative 0.5 for negative 1/2 to the k, just using that same letter for my index. My initial term, how did I know that? Well, I plugged in 1, right? Didn't we know how to plug in stuff? And we practiced that with sequences, not series? Did you get it?
What's the first thing on there? Like, something min equals 1. Was that
Oh, sorry. N min, remember, that's the lower bound. So the lower bound, sometimes it's 0, sometimes it's 1. In this case, it's 1.
What's an n?
Yep. Well, no, it's weird. In your calculator it is too. It's like italicized, I think, but it's awkward pixelated. Yeah. Now, I have my series over here. Do you guys see how I have my table set up to be ask? And I'm plugging in like, hey, what if it's the first partial sum, second, the 10th, the 50th, the 100th, the 1000th, you could keep on plugging in. What are you doing in your table when you're plugging in larger and larger numbers? Trying to predict going to infinity. Does that make sense? So you're predicting going to infinity. What do I see and what do probably most of you see seems to be happening? It seems that the series seems to be converging to. I think negative 3. It's okay, no judgment. Converging to negative 1/3. Seems to be, right? That's our prediction. But our prediction has a question mark because this is only a prediction. Number 2. Plugging in 1 over k. In a similar way, I only went to 100. Maybe you guys should go a little bit further because it goes from 1 to 1.5 to 2.9 to 4.499 to 5.187. It's growing, but it's growing by a half, and then it's growing by 1.4, and then it's growing by 1.5, and then it's growing by 1.6, and then it's growing by, maybe you guys should plug in like 500 or plug in 1,000. Is your calculator going to be thinking for a while, though? I'm curious. Has anybody tried plugging in a bigger number than 100? Take a second. My hypothesis is your calculator is going to have to be thinking for a while, which could be dangerous on an AP because it's going to have that little spinning wheel or dashy thingy of death. Because what is your calculator doing when you say go to 1,000? It's plugging in, finding 1,000, and adding them all up. Whew, that's a lot of math. Good thing it's the calculator and not us. See if you can see it converging at all. Are you serious? Oh, undo the alpha. There you go. There you go. Look at your cursor. If there's an A on it, it's an automatic alpha. You have to undo the alpha character. Oh, you have to use, that's always the N, but we're using it there, so you use alpha K. Yeah, to match up with your index. Just because, Justin, we need 2 variables because we need 1 to approach infinity and 1 to be in the summation. Oh, let me see. Oh, you got to get your negative in parentheses so that it's raised to the power. Does that make sense? Because PEMDAS says exponent, so it would do the n, and then it would just take all of that times the negative. But you need it to alternate. Now, the good news is, ultimately, this is not how we want to be solving these, like forever. This is ultimately not the goal, but it is going to be helpful for discovery purposes.
Is that wrong?
You gotta say, I need him.
Oh, those brackets.
Oh. You just use parentheses, right? You need brackets. But you need negative 1/2 to be the guy. Now try. Yeah, right? Yeah. Okay. What'd you plug in?
No, we just put in 100
Oh.
to see if we got it right.
No, but seriously, right?
Yeah, so
Okay.
it's just been-
So I was giving some tension because I wanted you guys to actually figure it out, how to use your calculator, and to also see that we haven't gotten very far. It's just 100, and like when we're doing limits for functions, 100 wasn't that big a deal, but for summations, it's going to take a while. And if you try to go to 500, I forget how long it took last year, but I had someone whose calculator was working for part of class. I think they went 500, someone else tried 1,000, and they just let it sit.
You might have ruined your calculator. But
Yeah.
1,000?
Yeah, right? Okay, so here's the dealio. Can we approach infinity with our TIs? In some ways, but it's still going to be limited. This one was pretty clear because the 0.33333s kept getting more and more and more fixed if you had plugged in more. So it seemed like this one's pretty valid. It seems like this one's valid. This one, does anybody want to take a stab at it, what they think it's approaching? It's diverging. It's diverging. Now, some of you, most of you, probably would have thought of something like, I don't know, 10, 9, 7, I don't know. Eventually, it's going to get closer, closer, right? Because you're adding like smaller and smaller fractions. What's this sequence converging to? Just the 1 over x or the 1 over n or the 1 over k? What's just that converging to? 0. So if it's converging to 0, you're adding smaller and smaller and smaller and smaller and smaller pieces. Shouldn't that converge? Mind-boggling. How about number 3? Plug it in, make a hypothesis. You don't have to go very high. Don't go to 100. Just go to like maybe 50 or something. Number 3, just go back really quickly. Change your formula to be 2 over k squared. 2 over k squared. Some of you are like, but it says n. Okay, you could do n, but carefully. You have to use a different variable up top. Yeah. So if it does put n, change it. If it does put n, change it to k, because remember, don't you need the n to be there so you can go to infinity? Sorry, Aryan, did you still have a question?
Yeah, we made the first one like exactly like what you have entered, and it's still not working. It's giving us like a pretty...
Oh. You have your k. You have your k. You have your n up top. You have your negative 0.5. Oh, no, 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 you're good. Your table just goes by ones. I had my table jumping. So I just plugged in stuff like, oh, instead of scrolling forever, I was like, what about 1 and 2 and 10 and 50?
How do you make it jump?
Table setup, ask instead of auto. Yeah, it's been a while since we did that. It was back limits, CalcAB. Have you guys seen the table? What's going on with number 3? No? If you plug in 1, it would just be the first partial sum, which would be 2. If you plug in 2, it would be 2 plus 2/4, 2 plus a half. I cannot do 10 in my head. E for effort. Anybody have decimals for me? Oh, I thought we had it. No? Okay, I'm going to keep playing. You guys have put this in, though, right? K equals 1, 2 over k squared, and you're trying to plug in? I can do this next in my head all day long, so I'll let you guys think about it. Because this one, aha, I like him. Plug in 0, that's 1. And then negative, and then 1, and then negative 1. And then this one's going to be 1, and then 0, and then 0, and then 0. I'm still looking for this one. I'm going to add in some things in here, though. Did anybody get this one plugged in? 3 point what? quiz we're predicting. Who knows if we're right or not? I've told you we're right on that one. I've told you we're right on that one. These ones I just put question marks. This one seems to be going up by 0.5, going up by 0.59-ish, going up by 0.15-ish. Like you might be thinking it's going to go up by smaller and smaller and smaller amounts. So maybe the partial sums are converging. Why on number 4, though, am I going to go ahead and put diverge? Even though if you did plug in my 10, 50, 100, 1,000, all of them would say 0, 0, 0, 0, 0, 0. You need to think about the odd ones, too, because it's going back and forth, 0, 1, 0, 1, 0, 1, 0, 1. Are the partial sums converging to anything? The answer is no way, Jose. Long story short, do we hope that there's something better than the calculator to do these? Yes. Okay, so let's talk about our very first convergence test. It's one you actually learned in pre-cal. We learned convergence and divergence in pre-cal? Yes, we did. Infinite geometric series. Sometimes they converge and sometimes they diverge. How do we know? It's all based on R. Infinite geometric series. Now, here's the bummer of this test. It only works if you're given a geometric series. If it's not a geometric series, you can't use the geometric series test. Oh. Now you are introduced to the dilemma of Chapter 9 OT. In our Chapter 10, like 2 sections. A sub 1. It's our initial term. Yeah. If you are given an infinite sum from k equals 1 to infinity, or n equals 1 to infinity, or I equals 1 to infinity, whatever, or 0 to infinity, of a coefficient times r to the k, this infinite series will always equal a sub 1, the initial term, all over 1 minus r, as long as r is in between and not including negative 1 and 1. The geometric converges, and not just converges, but converges to a sub 1 over 1 minus r, converges to the infinite sum if r is in between negative 1 to 1, and it diverges otherwise. Geometric series are nice, because as soon as we see it's a geometric series, we can know not only if it converges, but if it diverges. It is one of the rare tests that can show you both. Why? Well, because there's this thing called a common ratio. We talked about it last chapter in sequences, right? And so if you have an A1 plus an A2 plus an A3 plus an A4, if you notice that the terms are found by or related by or have a pattern of just multiplying a common ratio every time, there is this really cool formula in pre-cal in algebra, I guess, that says, hey, the nth partial sum, oh, no, that's the nth term. I already talked about that. The nth partial sum is equal to, oh, stink, now I have to remember, a sub 1 times 1 minus r to the n all over 1 minus r. This was a thing from pre-cal. First term times 1 minus r to the n all over 1 minus r. But guess what? We can go to infinity. But guys, what's the only time that this limit will exist? What happens if r is some sort of big number? When raised to powers, make it even bigger. Is this going to converge or diverge? Limit to infinity, degree test, who wins? Isn't the top always going to win as long as r raised to powers is getting bigger? So if r diverges otherwise, if r is greater than or equal to 1, or if r is less than or equal to negative 1, this limit will not converge. Only when r is 1/2 or 2/3 or 5/9 or 49/50 will raising it to higher and higher and higher powers actually decrease it. And only if we can get this to approach 0 can we get an actual sum. And the infinite sum will be zoop, 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 what you see. But that only works if the limit as n goes to infinity of r is 0. Congratulations, you have 1 out of 9 convergence divergence tests. You can deal with geometric series and geometric series only. This is endeavor number. We'll figure it out tomorrow. Guess what? We have one more test, though, to see, so make sure you don't skip tomorrow. Bye, guys. See you later. Maybe bring your calculator.